Let me thank the organizers for giving me the opportunity to talk about this long-running project of ours. The motivation for this project was to build simulations for open quantum systems in a recyclable manner. And the way C++ QED approaches this problem is that it defines elementary physical systems. We will see examples for what I mean by this, as building blocks for composite systems. And then it defines time evolution modules to simulate the dynamics of such systems. And the history goes back to my postdoc years at Innsbruck University. I started developing this framework in 2006. And at that time, we were looking at cavity quantum electrodynamics with moving particles, so CQED, and that's where the name C++ QED comes from. It's a C++ framework. But eventually, C++ QED saw a lot of more general applications in quantum optics, atomic and molecular physics, and some many-body physics also. But it's mainly useful for quantum optics. The fundamental design is motivated by quantum optics because quantum optics is the field where there is a great experimental control over the quantum states of individual quantum objects. So, for example, it's possible nowadays experimentally to trap a single ion in an electromagnetic field and have this ion in the ground state of the electromagnetic trap and have it for a day or several days, a single ion. And also this is also possible with photons. So between two very good mirrors, it's possible to trap a single photon of an electromagnetic field. And so there is a large demand for fully quantum simulations of these small quantum systems. And these systems are inherently open systems because even if we remove every noise source, the vacuum electromagnetic field, the vacuum of the electromagnetic field is still there, and atoms in these quantum states are sensitive to the presence of the vacuum field, for example. So these are inherently lossy systems. And then, so quantum optics deals with small quantum systems assembled from a few elements and with very well-controlled interaction between these elements. And these systems are now going into technology. So nowadays people talk about quantum technologies, and so there is a large demand for such simulations. So between 2006 and 2008, there was a version 1, but the version I'm going to talk about now has been developed since 2008. And the basic specification was to be able to simulate fully quantum open dynamics. So for example, a Schrödinger equation if the Hamiltonian of the system is given in a finite discrete basis, and open dynamics if the jump operators are also given in this same basis. So further specification was to have these building blocks, these elementary quantum systems, like a single electromagnetic mode or a single spin or a 1D motional degree of freedom. And then we can define interactions between these elementary systems, like an XX interaction between two modes, or a Jaynes-Cummings interaction between like a two-level atom and the mode. And it has to be very modular. So for example, if today I want to simulate a single atom interacting with a mode, then maybe tomorrow I want to be able to simulate this atom in motion also. So by adding a motional degree of freedom to this atom, I can use the same methods defined in the framework. So what are the time evolution modules? For open systems, a priori the master equation, the quantum master equation describes the evolution, but there is this crafty method, the Monte Carlo wave function method, which people developed to make systems larger systems more tractable. And then I can use an ensemble of several quantum trajectories to have an ensemble averaged state. So these are kind of the things that we use in general. This, for example, here this version of the time evolution naturally parallelizes, because I can run different trajectories on different cores. So we use supercomputers. We use this framework in several supercomputer environments. But unfortunately, we don't use GPU. We haven't used the GPU yet. But there is potential also for using GPU in the framework. Okay, so just in a few words, because not everyone is a physicist here. So the description of open quantum systems is one of the standard methods is the Born-Markovian master equation, and this density operator describes the full statistical and quantum state of the system. And the problem with this is that okay, this can be translated to an ordinary differential equation, which is good, because we know very well how to solve these. But the problem is that the density operator has the square of the dimensions of the state vector, and this makes it much more demanding to solve the master equation than a normal Schrödinger equation for a closed problem. Okay, so this is one example for an open system, just an electromagnetic mode interacting with the surrounding vacuum. And in this case, the openness of the system can be defined by these two operators, which describe photon emission from the mode and photon absorption into the mode. And so to solve this problem of dimensionality, people developed around the 1990s, these wave function methods, which made it possible to simulate open systems in the language of wave functions, state vectors, instead of density operators. And first it was, this method was proposed as just a computational tool to decrease the dimensionality of the problem. But eventually it was found out that this is also, this has also a physical meaning. So this Monte Carlo wave function trajectories have a physical meaning in the case when in an experiment there is full control over a single realization of a quantum system. So when it's possible to fully control a pure initial state of the system, and all the quantum jumps are also controlled, then these Monte Carlo wave functions are actually physical. So this is really what happens in an experiment, in such an idealized experiment. So basically, this is this makes the evolution split into two steps. So if I assume that there is a fixed time step, then first I have to take a coherent step with not with the original Hamiltonian of the system, but with a non-Hermitian Hamiltonian, which contains these jump operators. And after such a coherent step, I probe for a possible quantum jump with a probability that can be calculated from the result of the coherent step. And this quantum jump is corresponds to like observing a photon which the system emitted. Okay, and so this is as the name suggests, this is a stochastic method. So there is a trade-off. So this is a trade-off that we reduce the dimensionality of the numerical problem, but we have a stochastic problem in return. And the problem with this is that so we really like to use adaptive time step methods for dynamical simulations. And of course, we know that for ordinary differential equations, there are standard methods for this. But for stochastic problems, there are no general methods. For stochastic differential equations, for example, for adaptive stepping. But in this case, it was possible to develop an adaptive algorithm which was our contribution. Basically, what we do is that okay, for the coherent step, yeah, maybe it's worthwhile to note that this coherent step is also interesting in the sense that so even if I do not observe any photon, for example, so any quantum jump from the system, the system still feels that I observe it from the outside. So and this is reflected in this in that the evolution, the no jump evolution is non-unitary. So this method knows about this very quantum characteristic that the quantum state always, a quantum system is always sensitive to observation from the outside. So even if I do not, when I do not observe photons, this is also information about the system. And this is reflected in this kind of non-unitary evolution. Okay, so this non-unitary evolution can be basically driven by or simulated by an ODE stepper, which is usually we use a Runge-Kutta-Keskarp stepper, but over this we superimpose another step size control, which is basically that the overall jump probability in a time step has to be limited. So we introduce a maximal jump probability, and this is an additional parameter of our algorithm which controls the step size. Because this is actually a first order Monte Carlo method in the sense that in every time step we probe for the possibility of a single photon coming out. Whereas physically, of course, it will be possible that 2 photons come out in a single time step. But we have to make sure that the possibility of this is very small, negligible. Okay, I just mentioned that we have just published a paper about how this algorithm behaves as a function of this control parameter. So I can say that the behavior is very well understood by now, and we have a lot of experience with it. Okay, and one of the distinctive features of C++ QED is that we heavily rely on compile time algorithms. So as probably all of you know, C++ is a compiled language, but it has this interesting feature that a Turing-complete toolset is available at compile time, meaning that all information which is present at compile time can be arbitrarily processed. And for example, one toolset which implements this is the Boost metaprogramming library. This is what we used. It's a bit old now, but okay, the framework is also old. So the fundamental design principle was that all information available at compile time should be processed at compile time using template metaprogramming. And we hope and we experience that this makes the execution, so the runtime execution, more efficient. So basically, for a given physical system, we write a program, and all the information we have at this time about the system is optimally processed into the binary, which we execute to collect data about the system with many possible parameter sets. So this is the idea of the framework, basically. Okay, and I don't know if you ever saw this, but this is a classic example that template metaprogramming can be useful for physics. So, for example, with template metaprogramming, it's possible to teach C++ dimensional analysis. We can make it part of the grammar, basically, by defining types, like, for example, a force type or an acceleration type, or a mass type, and then it's possible to check the dimensional correctness of physical formulae at compile time. Now this is just a nicety. Okay, so the C++ QED has a hierarchical structure. So as a just an end user, an end user is presented with a rather high-level interface, but it's a C++ interface. It has Python binding, but still it's an API. But it's possible to go deeper. So for example, we do not need to use these elements I mentioned, like a mode, a qubit, spin, and the interactions. We can completely skip this part and go to the core, where we can just define Hamiltonians as matrices or as sparse matrices, and still we can simulate the dynamics of these Hamiltonians and Lindblatt's also. Okay, so, but on the highest level, basically, so the way we have to assemble these physical systems is that we select the free components that we want to use, and then we have to define the interaction between these components, and then there is such a graph of interactions between the free components, and this graph is basically processed at compile time into the binary which represents this system. And it turns out that for given problem domains, usually only a few physical elements are needed to, in order to cover this problem domain in quantum optics. This is the experience. So basically this program of using elementary systems seems to work, because only a limited number of elementary systems need to be defined. And this is how it actually looks like. So such a graph is represented by such a code in C++. And yeah, so it's, I think, rather terse, actually. And so far, about 20 research papers were based on this framework. So it's not a huge number. Unfortunately, to this day, C++ QED hasn't become very popular, but somehow people seem to be frightened by C++. This is my experience, and there are some alternatives in Python, for example, which are much more popular, but of course they are not so efficient as C++ can be in principle. So the applications so far ranged from polarizable particles in optical fields, ultra-cold atoms in optical fields, optomechanics or cavity optomechanics when we have like small mirrors or small transparent objects moving in electromagnetic fields in the quantum regime, and complex atoms in electromagnetic fields, eventually also with motional degrees of freedom. so it's possible to define any realistic atomic system, atomic level scheme within the framework. So it's possible to define those ions that they use in these ion trap experiments, for example. Okay. The implementation heavily relies on open source libraries like Blitz++, Boost, GSL, FLENS. And as I said, there exists a Python interface also. And the present problem, which nowadays really hinders the further development, is that the fundamental data structure, which is the Blitz++ library, is outdated, to say the least. I don't know if anybody ever used this. This is a famous, very venerable library, which was actually one of the projects where this template metaprogramming was first discovered. So it's arcane, basically. But it's difficult to find a replacement. The most promising candidate is this extensor library from the QuantStack company. Thank you for your attention.
So, any questions? If no, then I would have one. That you said that C++ seems to somehow scare people off. And do you think that it is part, I'm not sure how much the API exposes the MPL's angle bracket voodoo.
Yeah.
And I was curious if you think that somewhat more modern approach, for example, what HANA does, which completely makes do without the angle bracket notation. It looks a lot more like runtime computations. If that would help in this regard.
Yeah, probably. And also C++11, C++14 could help a lot, which I cannot fully embrace because of Blitz++. But sure. So this MPL, even though it doesn't appear directly in the highest interface, still it's kind of scary.
Okay. Any other questions? If not, then let's thank the speaker again.
Okay.